Okay, let's graph this thing. How do you find y-intercept? All right, so look at that thing, plug 0 in for x, what do you get? 0 over negative 1. I know what it is. I figured it out. Her mouth is faster than her brain. And she knows. It's just like the stuff comes out. It's like, totally happens. All right. 0 over negative 1 is, in fact, 0. How do you find x-intercept? We set the top equal to 0. So 2x squared equals 0. How many solutions will this have, by the way? It will have 2. And what does it turn out they both are? 0. So I'm going to make a little note here that I believe this is going to be repeated. Agreed? Okay, because that tells me something visually about how the graph is going to look. It's going to touch at the origin and then bounce away. Yeah, well, that's good. I don't want to, make you cry out of embarrassment or anything. I know. I have to add you to my tallies. New crier.
We have a first time, last time.
It was Riley.
Yeah. She cries like every day.
Yeah, she cried in study session the other day.
Yeah, she's crying today.
She cried today? Wait, whatever.
Yeah. Brittany and Maddie made her cry. Last day of math lab.
Wait, math lab doesn't exist anymore?
Just 4th period. For now. We're looking for a solution.
I've never been to homework ever again. Exactly. I've never passed in class.
Alright, let's continue. Discontinuities. How do you find discontinuities? So at the bottom equals 0. And what are all the types of discontinuities that a rational function can have? Poles and vertical asymptotes. That's it. So let's analyze this. X squared minus 1 equals 0. That gives me x equals 1 and x equals negative 1. Don't know which type they are yet. So the first thing, the easiest thing I can do to check is, do they also make the top equal 0? No, neither of them do. So that right there is proof that they're both what? They're both vertical asymptotes. So this graph doesn't have any holes. So we've got y-intercept, a repeated 0, a vertical asymptote. What is the end behavior? Look at the dominant terms. Divide the dominant terms. Yeah, when you divide the dominant terms, you get what? 2. So that is a horizontal asymptote. And the equation is y equals 2. Okay? So there's all the important information. The only other thing that I want to know that's going to help me graph this better is to actually analyze these vertical asymptotes a little bit more deeply. For example, I need to know on which side am I going up to a positive infinity, on which side, left or right, am I going down to negative infinity. So what is the limit as x approaches negative 1 from the left of this function? And what is this function? 2x squared over x minus 1x plus 1. So imagine plugging in a number that is just barely smaller than negative 1, like negative 1.01. Okay? So what do you get when you plug in a number just slightly smaller than negative 1? Well, what type of number is the top of this fraction always going to be? Always going to be positive. What type of number is this factor going to be if you're plugging in a number slightly smaller than negative 1? A negative. And what about this factor? A number slightly smaller than negative 1 plus 1 will be a negative. So what's a positive divided by a negative times a negative? A number slightly smaller than negative 1 is like negative 1.1. Right? It's not as intuitive, but a number smaller than negative 1 is like negative 2, negative 3. Okay. So this ends up being positive infinity. So as we approach that first vertical asymptote from the left, our graph is exploding up to infinity. So that's going to help us draw this. How about the other side of that same vertical asymptote? So what is the limit as x approaches negative 1 from the right? Well, we're plugging in a number slightly larger than negative 1, like negative 0.9. The top is going to be positive. This factor is still going to be negative, but this factor now will be positive. So that is negative infinity. Make sense? Now, how about the other vertical asymptote? What is the limit as x approaches positive 1 from the left? So we're talking numbers smaller than 1, like 0.9. Well, your top factor is always going to be positive. What's this factor going to be? Negative. And how about this one? So that will be going to positive infinity. And then what is the limit as x approaches positive 1 from the right? I believe all of the factors are going to be positive now, right? It wasn't. It was negative. Psych. And then this one's positive infinity. I was just seeing who's paying attention. Yeah. Okay. So now we've got a complete analysis that's going to help us graph this thing really, really accurately by hand. Agreed? So we've got a vertical asymptote at negative 1, positive 1, horizontal asymptote at 2, a repeated 0 at the origin, and that's it, right? And then when I actually go to draw the branches, I'm going to be using this data. For example, as I approach the left side of the vertical asymptote at negative 1, I need to go up to infinity. But then immediately on the right side, it's going down to negative infinity. Touch this x-intercept, bounce away, and then go down the left side of the vertical asymptote at positive 1. And then on the right side of 1, we're going up. And so that's a pretty good graph right there. Looks good, doesn't it? That is happy. Cool. Any questions on one of these? None? Good, let's do another one. How about x squared plus x minus 2 over x squared minus x minus 6? What's y-intercept? Plug 0 in for x, what's negative 2 divided by negative 6? 1/3. X-intercepts, let's set the top equal to 0. X squared plus x minus 2. So that factors down to x plus 2, x minus 1. So I got potential x-intercepts at negative 2 and positive 1. Do either of those numbers also make the bottom equal 0? Yes. Negative 2 does. So that cannot be an x-intercept. But does 1 make the bottom equal 0? No, so that is definitely an x-intercept. So we've got the point 1, 0. So you've got a y-intercept at 1/3 and an x-intercept at 1. That's it. Where is this graph discontinuous? Well, I have a prediction. It's going to be a negative 2, right? So when we set the bottom equal to 0 and solve, that factors down to x plus 2, x minus 3. So I have discontinuities. These are not potential. These are them. We have discontinuities at -2 and at 3. It's just a matter of what type are they. Let's start with 3. Does the number 3 make the top equal 0? No. So that is definitely a vertical asymptote. But we know -2 makes the top equal 0, so that we don't know about. So what type of discontinuity is there at -2? Is it a hole, or is it actually still a vertical asymptote? Could be. We don't know. We have to analyze further. Just because it makes the top and bottom both 0 does not guarantee that it's a hole. Okay? All that guarantee is that something cancels. Okay. Did we look yesterday at limits? Did I draw some weird graph that had holes in it and jumps and all this stuff and ask a bunch of questions about it? No? Okay. Let me think about how I want to do it. I don't know if that necessarily helps. Let's see. So here's the idea. Rational functions can have two types of discontinuities. They can have a hole, or they can have a vertical asymptote. Agreed? Okay. Let's suppose the x-coordinate here is -4, and maybe the y-coordinate here is 5, and maybe the x-coordinate of this vertical asymptote is 6. Does that sound good? And just for fun, let's also mark this point here. Let's call that -9, and let's pretend its y-coordinate is 2. Okay. So how many discontinuities does this graph have? 2. One of them is a hole, one of them is a vertical asymptote. Just for fun, what's the domain of this function? All the numbers except for -4 and 6. Great. If I were to ask you, what is f of -9? What's the answer? 2. If I were to ask you what is the limit as x approaches -9 of this function, what is the answer? So as my inputs get insanely close to -9, what do my outputs get insanely close to? 2. Okay? Was there anything weird going on in the function at -9? No. Whenever you have a function that is continuous through a point, won't the output of the function at that point be the same thing as the limit? Yeah. Okay? In fact, those are the easiest limits to evaluate. If I ever ask you on a quiz, what is the limit as x approaches 3 of x squared plus 2x minus 6, what would you do to find the answer? Just plug 3 in. Well, it's 9 plus 6 minus 6. The answer is 9. How did you know you could use direct substitution? That is the method we use to evaluate that limit. How did you know you could use direct substitution to evaluate that limit? It's a parabola. You know it's continuous everywhere. Okay? So the only limits that are difficult to evaluate that you can't use direct substitution on are the ones that when you use direct substitution you get something like 0 over 0. Right? Those are the really tricky ones that we need better techniques. Okay? So why do we need this? Well, let's analyze the hole in this graph. What is f of -4 for this function you're looking at right here? It is undefined. But what is the limit as x approaches -4 for this function? That is 5. Won't this always be the behavior when a graph has a hole in it? Won't a hole always be a point where the function is undefined, but the limit is defined? If you ever see a function where the function is undefined at some input, but at that same point the limit is defined, that has to be a hole in the graph. There's no other explanation for what's going on there, right? So whenever you have that, a point where you think it's a discontinuity, check out its limit. Because what happens at 6? What is f of 6? Also undefined. But what is the limit as x approaches 6? Does not exist. that limit doesn't exist. Because one, this is a two-sided limit. What's happening on each side? They're going in complete opposite directions. You can't possibly have a limit that exists when they're going in opposite directions. But the reality is they're going to infinity and negative infinity. Technically, that's a limit that doesn't exist.
I was supposed to say, so left-hand limit and right-hand limit on tests, are we supposed to say those limits?
If I ask you, like, if it's a two-sided limit, you have to write that like this. This is clearly going two different directions. But if I ask for a one-sided limit and you said negative infinity, I'd give you credit. To me, negative infinity implies that the limit doesn't exist. 5, though, is a totally different story. If you write an actual number, that's it. Okay? So here's the big thing. How can I tell if a function has a hole or not? By evaluating its limit. If the limit exists, it's a hole. If the limit doesn't exist, had to have been a vertical asymptote. So how am I going to figure out what our graph has at -2? By creating a limit and evaluating it. So the question becomes now, okay, how do you evaluate a limit? By hand, algebraically. What you do is, if it's possible, can I find a new function? And that new function looks like this. What is the only difference between the green function and the purple function? 1 point. There's only 1 point difference between the green function and the purple function. How would you evaluate the limit? So let's pretend the purple function is g of x. How would you evaluate the limit as x approaches -4 for the purple function g of x? By just plugging it in. Am I allowed to just plug -4 into the function g of x to evaluate that limit? Yes. Why? Because it's continuous. So, if I can find this new function such that the only difference, and let me ask you this, if the only difference between two functions is a single point, won't all of the limits between those functions be the same? Now, if I were to claim this purple function and this green function are actually the same function, would I be right? No. But if I were to claim that all of the limits of the purple function will equal all of the limits of the green function, would that be correct? Yes, because just changing 1 point isn't going to do anything to the evaluation of the limits. Right? So that's our goal. How can I evaluate a limit? Find a new function that fills that hole. So, we need to analyze what is happening at -2. And the way we're going to do that is we're going to say, what is the limit as x approaches -2 of x squared plus x minus 2 over x squared minus x minus 6? If I can evaluate that limit to where I get an answer like 5, then at -2 is a hole. If I try to evaluate that limit and all I can get is infinity or negative infinity or some explosion, then it is definitely a vertical asymptote. So how can I find, let's assume there's a hole at -2. How can I find a new function that is identical to this one but doesn't have that hole, fills that hole? Let's go back to elementary school. And your teacher gives you 14/6. And they ask you to simplify. And you go, okay, teacher, that's 2 times 7 over 2 times 3. And those 2's cancel. And so that's 7/3. Right? Is the fraction 7/3 the exact same fraction as 16/4? Or sorry, 14/6? Yes. They are. Well, guess what? That rule doesn't quite work for rational functions. Here we have this function x squared plus x minus 2 over x squared minus x minus 6. The top factors down to x plus 2, x minus 1. The bottom factors down to what? X minus 3, x plus 2. Are there any common factors that can cancel? Yes. The x plus 2's cancel. And so now I get x minus 1 over x minus 3. Here's a problem. Is the fraction x minus 1 over x minus 3 the exact same thing as the fraction x squared plus x minus 2 over x squared minus x minus 6? They're not. Whenever you cancel away a variable, you lose things. Okay? Hopefully you have seen this before in your mathematics career. Have you ever seen an equation like x squared plus x equals 3x? And people are like, oh, I'm just going to divide everything by an x. That gives me x plus 1 equals 3. So boom, x equals 2. Is 2 a solution to that original equation? Yes. Plug it in. What's 2 squared plus 2? What's 3 times 2? That's a solution. But guess what else is a solution to this original equation? 0. 0 squared plus 0, 3 times 0. So is this original equation the same thing as this one right here? They're not identical because what did I do? I divided both sides by x, a variable. Whenever you cancel away a variable from a math problem, you can lose some things. Did I cancel away some variables here? Yes. So what did I lose? I lost the whole. So for us, that's a good thing, right? What is the only difference between this fraction and this one? The only difference, 1 point. This one has a whole, this one does not. Okay? Yes?
How do you know things just change the whole?
Whenever you cancel common factors, you're guaranteed that, yes, you are changing the function. Potentially. Sometimes it actually doesn't. It's weird. Very complicated thing. Whenever you cancel a factor from the top and bottom of a fraction, you're only changing the function at most 1 point. So, yeah, maybe I didn't fill the hole. Maybe I changed it at some other point somewhere. But the key is, if I'm only changing it at 1 point, won't limits of this function, if all I'm changing is the function at 1 point, won't limits of this one equal limits of this one? Yeah. So what we do is we say, you know what? This is the function I want to evaluate the limit at, but I can't, because just plugging -2 in gives me 0 over 0. So instead, I'm going to look at the limit as x approaches -2 of this function. I know their limits will be equal, and this one's much easier to evaluate, because what can I do with this one? I can just plug it in. Now, what happens if you plug it in, and you still get 0 on the bottom of the fraction? It was actually a vertical asymptote to begin with. But in this case, I didn't, and that proves to me it was a whole. Does that kind of answer your question?
Yeah.
Will they all factor?
If you get 0 over 0, something will factor and cancel, yes. Yep. So now we plug -2 in, and we got 3/5. So that not only proves that it was a hole to begin with, it also gives me the location of the hole. It has coordinates -2, 3/5. Right? Okay. So I took a long time explaining it, so it might be confusing, but we'll go over it. The only other thing I should do before moving on is analyze this vertical asymptote. Do you always, is it always essential to analyze this vertical asymptote to know how the branches get drawn? Not always. Sometimes through other logical reasons, you know there's only one possibility. Well, yeah. So let's see if we can do it without analyzing the vertical asymptote. So let's see, what information do we have? We have a vertical asymptote at 3. Bam. Oh, I forgot end behavior. What's the end behavior? Is there a horizontal asymptote or not? Yes, there's a horizontal asymptote at 1, because x squared divided by x squared is 1. There's an x-intercept at 1, 0, a y-intercept at 1/3, and we've got our hole at -2, 3/5 right there. Do you feel like you are confident in knowing which way we're going to be going around the asymptotes? Like, is there any way my graph could look like this? How do you know? Oh, you're allowed to cross horizontal asymptote. Why isn't this scenario a possibility? Well, I just messed up the drawing. Well, let's pretend that's round. Again, I just drew it wrong. Technicality. If it touches here and bounces away, then that number should have shown up how many times as a 0? Twice. Did it? No. Okay? It's got to cross through there. And can it cross through again? No, because that's the only x-intercept. It's the only one, and it is not repeated. So it's going to cross through and not go back up. Right? And so therefore, the only logical possibility is that it's actually approaching from the left. Now, ultimately, what's the only way we know that for sure? We should have evaluated the limits for the vertical asymptote. What is the limit as we approach 3 from the left of this function? And we would have gotten negative infinity. It's the only way to truly know for sure. And then on the right side, could the graph look like this? How do I know that's impossible? That introduces a new x-intercept that I didn't find. I know there's no other x-intercepts besides 1, and that's it. So that can't be. So it has to be up here. So there are logical reasons why that's the only possibility. So I didn't need to analyze that vertical asymptote. But I would say, better safe than sorry, analyze that, because sometimes some people don't get that logic, and that's fine. What does this look an awful lot like? Something we learned how to graph last Thursday. Yeah. Hyperbola. Yeah, well, don't be surprised. Simple rational functions, right? Which the graph shape is called a hyperbola. Doesn't this look a lot like a simple rational function? But what's the only difference between this and a simple rational function? There's a hole. What simple rational function is it this guy is really trying to look like? X minus 1 over x minus 3, that one that we simplified down to. If you were to graph that function on top of this one, they would look identical, except this one would go right through the hole. The only difference.
So are you going to tell us to, like, take this simple rational function and write an equation for it with a whole negative?
Oh, I've never asked that before. That's a good. I like that. That's a good idea. What? That's a good question. That's good. That's not hard at all. Say, take the simple rational function x plus 5 over x plus 3 and make it have a hole with x coordinate. I don't know. Pick a number. Make it have a hole with x coordinate 2. Then what do? You just multiply top and bottom by x minus 2. Boom. If you were to graph that thing, it would be a simple rational function with the whole x coordinate 2. Okay. Questions? Questions? Okay, let me show you some, let's create a rational function. Let's say f of x is x squared minus, no, I don't want to get crazy on you yet, x squared plus 6x plus 8 over x squared minus 4. And I don't want to do the full analysis on this. You guys are getting pretty good at that. But are there any numbers that make both the top and the bottom of this function 0? Which would be what number? Negative 2. Negative 2 makes both the top and the bottom 0. If you plug negative 2 in, that's 4 minus 12 plus 8, that is 0. 4 minus 4, also 0. Okay, so we have a 0 over 0 situation, or as a professor I had in college called it, 0 low over 0 low. 0 low. And he also called it Snope. I don't know why. 0 low Snope. Interesting. Really didn't like that professor. I don't think he liked me. I argued with him all the time. So, the number negative 2 causes 0 over 0. Agreed? So, that could be a hole, it could be a vertical asymptote. Let's evaluate the limit. What is the limit as x approaches negative 2 of x squared plus 6x plus 8 over x squared minus 4? Well, we're going to use the factorization technique. The top factors down to x plus 2, x plus 4. The bottom factors down to x plus 2, x minus 2. So that factor cancels, and I end up with the limit as x approaches negative 2 of x plus 4 over x minus 2. How do I evaluate that limit? Direct substitution. Negative 2 plus 4 over negative 2 minus 2. The answer is negative 1/2. So what type of discontinuity did this graph have at negative 2? It was a hole. Make sense? Okay. We call this technique, there are lots of techniques used to evaluate limits. When you take calculus next year, you're going to learn direct substitution, which you've already learned. You can only use that if the graph's continuous. You're going to learn the factorization technique, which is actually what this is. Yes, I can't use direct substitution, but if I factor and cancel the thing, can I use direct substitution on my new fraction? There's something called the rationalization technique, which is when radicals are involved, and you got to multiply by conjugate, and get real nasty. There's something called L'Hopital's rule. The Marquis de L'Hopital was like a member of French royalty, and he really wanted to be a smart mathematician, but he wasn't actually. So we actually hired the Bernoullis. Ever heard of the Bernoullis? This family of mathematicians and scientists. You should have heard about them in science class. Hired one of the Bernoullis. I don't remember which one. There's like 5 of them. They're all geniuses. And the Bernoullis were a personal tutor to the Marquis de L'Hopital and taught him mathematics. And the Marquis decided, you know what, I'm going to publish a math textbook. And so he publishes this book, and on the first page of the book, he says, you know what, I got a lot of help from one of the Bernoullis, so anything that they claim was actually their original work is their original work. So he left it up to the Bernoullis to claim what was truly their work. And so he publishes this book, and in this book is this great mathematical discovery that we now call L'Hopital's rule, even though the reality is, who probably discovered it? One of the Bernoullis. Well, none of the Bernoullis ever claimed the work as their own, and they actually died pretty soon after the book was published. So nobody knows for sure who really discovered L'Hopital's rule. I know, it was not L'Hopital, he's a fraud, but it's pretty interesting. But we call it L'Hopital's rule. That's another technique for evaluating limits. All we're going to learn right now is the factorization technique. Okay, we might learn the rationalization technique at the end of the school year in May when we start actually learning calculus. But for now, just factorization technique for evaluating a limit. It's actually 2 techniques combined, right? It's using factoring and canceling to create a new limit that we actually solve using what method? Direct substitution. Okay, here's another one. Let's do x squared minus 9 over x squared minus 6x plus 9. Can you find any numbers that make both the top and the bottom equal to 0? 3. So let's evaluate this limit. What is the limit as x approaches 3 of x squared minus 9 over x squared minus 6x plus 9? Well, when we factor this thing, we get x minus 3x plus 3. The bottom gives me x minus 3, x minus 3. So when we cancel a common factor, we have the new limit for what is actually a new different function, but I know its limit will be the same, x plus 3 over x minus 3. So now how do I evaluate that limit? Oh, you can't use direct substitution. That gives you 6 over 0. That means this limit actually does not exist because you get 6 divided by 0, and that meant that that was actually a vertical asymptote to begin with. Any non-zero number. Here's the thing. After canceling, is there any chance after canceling you end up with 0 over 0 again? No, not if you cancel properly. I mean, if you factor and cancel all the common factors, you should never get 0 over 0 again. You either get some number over some other number, and that's a whole, or you get some number over 0, and that's vertical asymptote. What if you get 0 over some number? That's a whole, but it's a whole right on the x-axis. It's still a whole, but it's right on the x-axis. So it's kind of like a deceiving x-intercept. Does that make sense? So you'd still just treat it as a whole. So basically the idea is this. If you get a number in the denominator, it's a whole. If you get 0 in the denominator, it's a vertical asymptote. Cool? So I guess, here's the interesting thing. What is the only difference between this function, if you were to graph it, and this simple linear function here, if you were to graph it? You're telling me x plus 3 over x minus 3 doesn't have vertical asymptote at 3? There actually is no difference between those two. Okay? Isn't that weird? Those actually are exactly the same thing. Because you're not filling a hole. You're not adding a single point into the graph. Canceling that common factor didn't actually do anything. We actually classify discontinuities. There are two types of discontinuities. There are discontinuities that are called removable, and there are discontinuities that are called non-removable. What type of discontinuity do you think a hole is? It's a removable discontinuity because when you cancel, you're adding a point to the graph, and that discontinuity just went away. What types of discontinuities are vertical asymptotes? Non-removable. No matter how much factoring you do, that vertical asymptote is still going to be there. You cannot remove it. Does that make sense? So what did this canceling here try to remove? It tried to remove the vertical asymptote, but you can't. And so actually you end up with a graph that looks the same as the one you started with. Whereas up here, we actually removed the hole. So this graph is just barely different than this graph. Barely. 1 point out of infinitely many. So what percentage of the graph is actually identical? Approximately 100% because 99.9999999999999. What is 99.9 repeating forever and ever and ever? It is 100. But there is 1 point difference. How can you count it to infinity? Not my brain hurts. I don't know what I'm talking about. Okay. Any questions about holes? We'll call it a graph with 2 horizontal asymptotes. We'll call it today. We've been working on the same homework since last Thursday, and we are finally done. So I should be able to collect this tomorrow, and everybody should have it, right? We've been working on it since Thursday. Now, tonight, though, I want you to put some effort into it, because now every problem in there that has a hole, you should be good at. So we're ready to move on to section 2.7 tomorrow. Come in with your long division hats on. Luckily, everybody loves long division.